So I wanted to go over a few of these problems in a little more detail, especially the random walk um, and how we select sample this probability distribution. So let's actually just start with the random walk with the coin flip and let's just look at the probability distribution. What would that probability distribution be? So, put that there. So let's graph that. So a random walk has two possibilities. We go at -1 and 1, right? And they're coin flips. So let's say put zero point 0.5 there, that's a half. So there and there. So we have two possibilities. This one and this one, the probability is 0 everywhere else. This is our probability function of our distance, and then this is the distance traveled. Now let's look at the cumulative distribution. And let's see, we have half, 1, -1, 1. So 0, we hit the 1, we get a half. All the way here, and then we hit the 1 right there. This is our x, and then this is our cumulative distribution. So we can't move anything less than -1, so there's 0 cumulative probability there. We hit 1, 50% of our probabilities would be used up. So we go there. And then we don't gain any more probability because nothing happens till we get to 1, and then that's all of it right there. So you can kind of see if we have a random number. Let's make this a little better here. So if we have, put that 1 there, C, D, F. So our random number generator goes from 0 to 1. And you say, okay, if we have a random number that's from 0 to 0.5, say 0.2, which right there, where does that lead to? Boom, 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 to this. And we move -1. If we have, say, here, boom, 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 bink. So that's 0.4 -1. But if we have like 0.8, tink, we go over and we move 1. So whatever probability, whatever our random number is, we come over here and it decides how far we're going to move. So this is when we talk about inverting the cumulative distribution. So our CDF, let's just write it out. It's 0 when x is less than -1. It's 1/2 -1. Okay, -1 less than equal to x less than equal to 0.5, and then it's actually the x equals to 1 here, and then it's just 1 when x is greater than 1. Right, so 0, half, and then 1 for all eternity. We've used up all the probability. And then we've kind of just talked about the inversion of that. So if our random number, the CDF is our random number R between there and R. So if R is less than or equal to half, then that means x equals -1. If R is greater than half, x equals 1. So if R is in here, and if R is in here, 1. Simple. Okay. So and then this becomes our answer for the random walk. And so now we have a if statement. So you make the call on the random number between 0 and 1. If it's less than 5, you move -1. If it's greater than 0.5, you move +1. Easy. Let's go ahead and erase everything. And let's look at the example problem that I have in the notes. So it's the same thing here. So we have a probability distribution of x1, was it 1/3 x squared? So let's solve the CDFs. Now the cumulative distribution function goes from -infinity to our x, px, delta x. In this case, everything starts at 0. Before that, everything's 0, so we can rewrite that as 0 to x, 1/3 x squared. This 1/3 is for normalization. Dx, which equals x cubed. Right, x cubed. 1/3. Wait. Oh, that should be a 3. What am I doing? The 3 is for normalization. I was like, well, I know it was 1/3. The 3 here is for normalization. Okay, plus a constant. So that's our CDF. Now, see here, you got to make sure that this whole function, so at the start, there should be 0 probability, and then when you're done with all the possible actions, you should have a probability of 1, right? Because you're adding up all the probability of the possible actions. So our first one's at our start of our thing, of our region of action here is at 0. So if I put 0 in, C must be 0, and then this goes to 1. If I put 1 here, x cubed is 1, so C equals 0. So that means finally our CDF equals just x cubed. And then the CDF, the actual CDF becomes our random number r equals our distance cubed. So we invert that. So x, the distance we're traveling, it's going to be r, 3 power. Now in your homework, make sure that our CDF here, at the 2 limits, the lower limit where we start all the action is 0, and then the upper limit when we've done everything, or all possible moves have been made, equals 1. And if it's not, then add C accordingly. Make sure it's normalized. But then this becomes our answer. And we could, if this was the rule we were following to, we could program this in, right? Because we're always going to call this r between 0 and 1, and you just put that here 1/3, and you spit out your answer. So here's a function right here, right? This is telling us a function we can use where it calls the random number from 0 to 1, and then outputs x based on this here. And again, we could look at this with our 3D random motion, our spherical 3D random motion, if we want to do spherical random motion. So if we're doing 3-dimensional random motion, say on a grid or something, we could say, okay, you could look at the volume element, right? So dv, this is, so if you do an integral, you're filling, when you do the integral with the volume element fills the volume equally. So in Cartesian, it's just dx, dy, dz. So you don't have to do anything here, right? The thing that's being differentiated is our probability distribution. So x could be whatever distance. If we're traveling, say, any distance between -1 and 1, well then x could be -1 and 1, y would be a probability distribution, so on and so, it would be -1 and 1, so on and so forth. But if you do it in spherical coordinates, when we have r squared sine of theta d theta phi dr, and then theta goes from 0 to pi, and phi goes from 0 to 2 pi. That's the range. We've got to be careful because we're not just differentiating d theta here, we're differentiating sine d theta. And since I'm giving you the r distribution from, it's going to be the probability distribution of our random walk. So this is our d theta. So r is going to be just go from -1 to 1 or 0 to 1 based on the probability distributions from the previous particles. We're really only interested in the theta part, or the angular part, the d theta, d phi, the square angle, or the stair radiance, as it's called, which is given this symbol, which is this, sine theta, d theta, d phi, also ranging from there. So nothing's being differentiated here, so we could just say, okay, we can just select a random number from 0 to 2 pi, and we'll select that right. But we got to be careful here, because what you could do is you could rewrite this all as d cosine theta d theta, and then the d cosine theta ranges from 0, 1 to -1, right? So what I do is I can make a call from 1 to -1 and 0 to 2 pi, and that's the random cosine theta, and then I could do arc cosine to get my random theta. So we'll actually do that. Okay, so we have random number 1. So our radius is taken care of by the probability distribution, but we have to make 3 random calls. Here we could have done, if we're doing Cartesian, just a random call for x, y, or z. Here we're going to do a random call for r, which is taken care of in the homework problem, and then a random call for theta and phi. So we'll do a random number, and that will range between -1 to 1. How would you do that? Well, you'd have hold on a second. So we're going to make a random call from -1 to 1. So we'll call that random number, random 1, which that will equal. So then that means R1 would equal 2 times the random number generator. So this random number goes from 0 to 1, and then -1. So if this is 0, we get -1. If this is 1, that's 2, -1. So that gives us our range. So that's, and then we have so that's our random cosine, and then our theta would be our cosine of R1. So that's our random theta. And then our random phi would just be simply 2. Our random phi would just be 2 pi r, where this random number is from 0 to 1. So let's box that in. So what we're really doing is we're calling a random cosine from -1 to 1, which is using the random number, our random number generator, this one here. And then we also call it again from 0 to 1 for the 2 pi. So that's how you do, that's how you sample stair radians in a random matter uniformly. So let's go ahead and look at our code then and see if we can actually implement some of this. So here's the template I gave you guys. I already built it, so Let's rebuild it. Just make sure everything's okay. Yeah, it gives me this warning here because I is not actually used. So unreferenced local variable is not used. We're going to make, say, a bunch of random walkers. So we can define n, say 100 right now, but this will be 1,000,000, whatever. And they're going to take values, since we're sampling random numbers, and not always -1 and 1, let's just make this a double, and I'm going to actually allocate that double. We'll get rid of this for now. Well, let's keep this. We'll call an R, we'll call this R now. So our random number between 0 and 1 is now just called R. So let's remember, if we can remember our malloc, our memory allocation, X equals double malloc. So the malloc, its input is, it wants size in bits. How many bits are we setting aside? Well, that's where the size of happens, right? So n is the number of elements, and then each element is in bits the size of a double. Okay, I think that's right. Field solution. Good. Yeah, and then of course it's always a good idea to just go ahead and just for fun, good practice to initialize our array. And we're going to set all our random walkers, our 1D random walkers, to 0. So they all start at the same spot. So this will be random motion or random diffusion of how many little particles we have, or molecules, and they all start from the 0. So like I put a little drop right there at x equals to 0. They could go minus left or right. Okay, so let's actually sample from our random distribution. So we have several random distributions that we can sample from, and we're moving through time. So let's have a time variable, call it t, and we have, say, yeah, time variable t. So let's set up the motion of our guys here, of our walkers. So it's going to be an embedded loop, right? We're going to have a time loop. So t equals 0. T is less than. So this could be a variable, or you just put a number here. I'm going to just put 1,000, 10,000, 5,000, whatever the assignment asks for. So that's how many time steps we're going to do. In this case, we're doing 1,000, and each time step we need to update all the little random walkers. So that we just copy and paste this guy here. Obviously, we're not setting them all equal to 0. We're updating the position, so that's the position they already have plus some distance. Right? We don't know what that is. So this is where a function is going to come through. So let's make a function, and that function is going to be the one that samples. Now you could set up this function that has cases where you say, okay, I'm going to do problem 1, so you just say, you just input problem 1 as an input to this function, and it'll do that probably distribution, I guess problem 4 or 5 here. So let's set that up. So this is going to return a double. This is going to return the distance we traveled. We might as well call it distant. And let's input an int, and that input is what case we're going to do, what type of the function. Oh, it doesn't. Case is an actual thing. What do we want to call this? Call it k. Whatever. We want to input some integer, and we can actually set this up right now. and it's going to be the first, right? And the first one we're going to do is the coin flips. So there we go. And it's given, oh no, you haven't actually done anything yet. So let's actually code this function. So you just copy and paste this. It's the same, everything here. So, and really, let's see, this should be at the top, right? The first thing you should do is do your seed. So we define the seed here. Okay, so we have that. I don't need any of this anymore. I don't even need R, so double R. And then let's cut this guy out. So let's trim things here. So R is a random number. We need this, but we don't need this here anymore. Okay. Yep. And we have distance we're going to travel. And that's what we're going to return. So initialize it. If you return a variable that's not initialized, it'll cause major headaches. So just go always start that. Just in case something's wrong in your code and you don't actually set this equal to something, it's always just set it equal to something right away. In this case, everything will be fine. Okay, so there's a couple ways we can do this. We could do an if statement and say if k is 1, and then do our coin flip and do the random walk, and if k is 2. So we could just say, hey, if k equals 1, and then do coin flip. That's fine. And then you could have an if k is 2, and then in the 2 case, go ahead and do problem 5. That's perfectly fine. You can have a bunch of if statements. There's another way to do it. It's called that I'm going to show you. It's called a switch case thing, and it's just the same as the if statement. But it's like an if statement, but you have more. It's like a switch. Like I put the dial at 1, 2, 3, 4, and I don't have to make a bunch of ifs and then ifs and ifs. And it's the setup's a little funky. It's switch case. So you start with switch, and when you hit that tab, it already starts to fill stuff in. And what this thing is going to read in is our k value, right? And then we have to give it cases. So it starts with the default. Default means k here isn't one of the cases, so it defaults and says break. So let's it should also print an error message, right? Print f pick a case 1 or 2. We're going to only have 2 here, right? And then new line. Because if I put 3 in here, or if I put anything in here, I haven't set up any of the cases. But if I put like a 3 or something, it's going to go to the default. Default is a catch-all for anything you don't define. So let's do case as 1. So, and then colon. So if k here, this thing here is 1, it's going to hit this case, and then we need a break. Each case needs a break. Let's put a tab there. Oh, yeah. So, okay, so case 1 is the coin flip. So we're going to call RR a random number. If R is less than 0.5, distance equals -1, semicolon, else distance equals 1. So that's our coin flip case. And then break. And then we need a new case. Case 2, colon. And then always have each case ends with a break. So why do I break? Break breaks out of the loop. So if I don't have a break here and I say case 1, it's going to do all this, no break. So it's going to go here and start running all this stuff. So you have to have the break. So case ends with a break. And then this is the code. So this here is going to set the distance. Yeah, so this is our coin flip. Here, we got case 2. So this is where you put the solution to problem 5. Okay. So there you go. So I'm returning a double, that's a distance. I'm going to set that, initialize that to 0. Because if I don't hit one of these cases here, and this isn't initialized, it's going to, and so it's going to return some null value that's not a double, and it's going to cause your whole program to crash. So just always initialize variables that you're going to return. And I have case 1 where I give you, that's just our standard coin flip. And then case 2, it's up to you. Find the cumulative distribution and invert it. And you'll have 2 cases since it's a discontinuous function. It's a triangle function, so there'll be a bunch of ifs and stuff like that. But it's almost very similar to this. You'll have 2 regions you'll have to define. Okay, so let's put a breakpoint and see how this works. So we are doing case 1, so it should go ahead and hit this. So let's go ahead and start debugging. So, okay, I'm going to start. You can step over here and it'll just step into the code. Actually, let's put a breakpoint here. Okay, there we go. Now we can step into it. So, K is 1. So it should hit this. Let's see if it hits that. Oh, it did. It went right into there. Found an R. R is less than a half. So it should hit this if statement. It does. You see after that, our distance is -1. Hits the break statement at the end. Goes right to the return. Good. Works exactly like that. It's a return distance of -1. Okay. We'll do it again. See if we get, what's R? R is greater, then we should hit the other. Boom, distance is 1. Sets it, see it right there. Good, everything's working. Everything's working. And just for curiosity, let's put something that doesn't make any sense. We have case 5. So this is a point where your code doesn't have to answer all the questions at once. Here I have set it up where if I complete this function here, that I could do problem 4 and 5 with one code. So I could just do, okay, this one, problem 1. So you could just say, hey, in my code, I switched between case 1 or 2, and that's how I found the data for problem 4 and 5, right? You don't have to section code that's specifically, oh, this is problem 1, this is problem 2. No. That's what your write-up's for. The code is to get the data. So it's to do the simulation. And then from that, you can go and do the analysis in like Excel or something, make figures and do all the analysis and do your write-up. So this is a nonsensical case. Let's start debugging it. Let's see if it hits that default. Oh, I forgot my breakpoints. Okay. So it's just a bunch of error statements. Oh, I guess it just, okay, man. Okay. So you saw it stop, hit a bunch of error statements. Okay. So that's essentially a good setup uh, to do the simulation. So that's the setup for problem uh, uh, 4A. And then you could actually have a function that takes another function, let's minimize this. So then for like finding the standard deviation with time, you could have another array that's how many time steps big, and then just measures that standard deviation every time step and writes that to an array, and then print that array to a file, and then you can make a graph of the standard deviation with time. Easy. And then when you're doing this one, you could have a function that gives you your stair radians. So you could say, okay, here's my random, or you could even make it another case, like a case 4 or 5, or 3 or 4, that does your theta and phi a random selection. Yeah, so, and let's look at this guy here. So this is more of an analytical thing. So we're going to start, so this is actually, you give it a concentration, which is like, I have 1,000 random walkers that start at 0. And then I'm going to use this equation, this master equation here, which is just another rewritten of Fick's law. I'm going to use Fick's law to determine where my random walkers go. So let's start a new notepad. Okay, so let's say we start at time 0. Oh, it's not working. Okay. And my tablet's not working. Let's pause for a second. Okay, so we're back. I had a problem with my tablet here. So very similar to our random walk, but we're going to use the Fick's law to actually determine the motion of the particles. So we're going to start all of our random walkers however you want, 1,000,000, 100. You probably want to start at 0. And then they're going to sample Fick's law here, which has, you see here that we have, we differentiate time. So we have so we're at position X, so the random walker at position X at its future time, t plus delta t, is determined on its current time's position, so where it's at, plus your diffusion constant and all that here, but it looks at its side positions, position left and position right. So we go here. So what we're going to do is very similar to a random walker. We're going to sit here. So okay, let's do that. But you need a little more. So here, say, is, we'll break this out. So this is our X. So our random walker is here, and the concept, the Fick's law that the differential apart, we need to know what's here and here. So this is its position now, and then our position in the future will be right here. So this is t plus delta t, and this is, x, your position, and then this is the current time. So we're at this guy, and we want to update its position. So it's going to scan. So it's going to scan this here, and this here, because this is x, x plus delta x, and then x minus delta x. So you kind of see already that this necessitates 2 arrays one for our current time and one for our future time. Because if the future time scans itself, so I update this guy, and he's going to get it. So I come here and I update this guy, so this guy gets filled in. And this is a new updated quantity. You don't want this guy to scan this. So let's say we have numbers here. We have say 5, 2, and 3. And then I go here and I update this guy to 6. Now when I get here, I don't want this to see 6. I want it to still see that 5. So I need an old space and a new space. So what I would do is have an array, 2 arrays for this problem. I'd have an array, call it X, and then it'll have your n number of random walkers, and then another one that says X new. And what happens is, so you put so at the starting point, all n are at 0, right? So here. And then X new is going to go and scan. It's going to scan, see these guys, scan, and then that's the new, and then puts it all here, and that becomes the X new. And then the new times, and then at the new iteration, the next time, you're going to just put all these values into here, and then rescan. So you make a new X new by scanning over the space. That becomes the new time. Increment time. When you increment time, you just go ahead and copy all these values here, and then do it all over again. And so you have an array here that holds this as your X new, and then that scans your current time, you're just X. So so these two here are your current position, and then the adjacent positions are taking care of these terms. So a new space and a current space. So this takes 2 arrays. And your D that you input here is just going to be a number that you found, say, from problem 4 or problem 5. Set your delta X to 1. Your delta T can be 1 or less. Actually play with delta T and see what you get. Okay, that's it for this video. If you have any questions, email me or ask me in my office. And good luck.